Good morning, everyone, and welcome to today's webinar by X-Rite Pantone. Our expert will guide you through the steps to define a realistic pass-fail tolerance. My name is Jessica Hilaert, and I am Marketing Manager with X-Rite. I will be your webinar moderator for today. During the webinar, we will keep everyone muted. However, you will have the opportunity to submit text questions to today's presenter by typing your questions into the questions pane on the control panel. You may send in your questions at any time during the presentation, and we will collect these and address them during the Q&A session at the end of the presentation. You will also receive a follow-up email within 48 hours with a link to view a recording of today's webinar. I would like to introduce our presenter of today's webinar, Colin Wakeford. Colin gained an MPhil in color chemistry from Heriot-Watt University and since then has amassed 30 years of experience in the color industry. As an application engineer for Greta Macbeth and then X-Rite, Colin works across various industries, including paint, ink, and textiles. And now I give the word to Colin, wishing you all a very interesting webinar. Hi, Colin.
Good morning. Or should I say good morning, good afternoon, and good evening. I think we have quite a wide range of attendees today. So hello and welcome to the realistic pass-fail tolerance presentation. So as probably all of us know in our different industries, color is becoming increasingly important. Our customers are becoming more literate about color. Their expectations are becoming higher across the plastics, textiles, ink, coatings, and many other industries as well. Research has shown that people will make up their minds about the purchases within about 1.5 minutes of the initially looking at the product, and 90% of this will be based on the color specifically. So first question to our attendees for today. How do you assess color? Are you doing it visually, using instrumentation, or are you doing a combination of visual and instrumental color assessment?
Okay, we're launching the poll question. Everybody, you have a few seconds to answer. Okay, let's wait. Okay, a few more seconds. Okay, I'm closing the poll and we can analyze the results. Here you go. Colin, can you see the results?
No, not at the moment.
We have 88% that are using both, 6% visually and 6% instrumentation.
Okay. Well, that's it means that the next few slides will be quite familiar to the majority of our audience today, which is good. And obviously, for one or two of you, it will be new. So,
we're back to
Jessica,
your presentation. Yeah, you can go on.
Thank you. Okay. Okay, so color measurement metrics. So if we are doing instrumental color assessment, what numbers are we looking at? What scales are we talking about? So probably for many of you, you will be familiar with the C-Lab equation, which has probably been the most commonly used across most industries since the late 1970s. So here we have 1976, the CIE published the C-Lab color space, three-dimensional space into which all colors we can see can be plotted in terms of the lightness, red, green, and yellow, blue coordinates. Obviously, within this space, we can also describe these coordinates, again, in terms of lightness, but also the chroma or saturation and the hue angle. So just to illustrate that these values, these CLAB values, if we obviously we measure the spectral reflectance using our spectrophotometer. That is, if you like, the raw data. That data is then manipulated using the illuminance that we have chosen to assess the color under. In this case, we have D65 and the standard observer function. Obviously, that depends whether we are a printer working within print packaging, for example, who would use a 2-degree standard observer, but most of the rest of us who are in textiles, paint, plastics, and other industries would use a 10-degree standard observer. Obviously, there's also a number of different daylight standards. So again, depending on the industry we're in, that may differ very slightly. So we have to be very clear when we are setting tolerances that we establish and make very clear in our supply chain exactly what color equation we're using, also the standard observer function, and the exact illuminant or range of illuminants we're looking at under. So here we have a color under 10-degree standard observer, D65, with a lightness value of 39.9, A star value of 48.03, which means it's very red, and a B star of 17.17. Again, it's in the positive direction, so it's a yellow. So even if we did not see the color swatch, we could say here that we have a color which is in the red area and probably yellow shade red. So we have numbers which allow us to communicate on a simple level with each other the type of color we're talking about. Obviously, what this also helps us to do is to check how a color will appear under a number of different lighting, in this case, lighting conditions, which we refer to as METAMERISM. There are different types of METAMERISM, but today we'll concentrate purely on changing the illuminant. So here we have a plastic bottle under D65 daylight on the left-hand side, and cool white fluorescent, or F2, on the right-hand side. And we can assess by purely looking at the numbers or using a light box or both, whether this color will change significantly as we change lighting conditions. So if we look at the numbers here, we can see under daylight, we have the CLAB values. Under the cool white fluorescent, the L star value is almost exactly the same. The B star value, the yellow blue, again is very similar, but we have a significant change in the A star. We've gone from 48.03 to 37.77. So this bottle will appear 10 units less red under the fluorescent light. So obviously, if the specification is for a very bright red under fluorescent shop lighting, then this formula that we're working with probably is not suitable. We would have to look at a formulation that maybe has a more vivid red or more yellow shade red, for example, in the formula to maintain that intensity of the red color. Okay, if we look at these 3 dimensions, the L star, A star, and B star, in the 3-dimensional space, if we compare 2 color points, we've got a delta L star, a delta A star, a delta B star, and if we, using the CLAB equation, which gives us the square root of the sum of the squares of these 3 dimensions, we get the delta E star, or the color difference. Again, we have to be quite specific here because unfortunately the color scientists in their wisdom have used delta E for all the color equations, delta E standing for color difference, but we then have to be sure that we're talking about delta E star, CLAB, or delta E76 as some people refer to it, or some of the other equations which we will touch on later in the presentation. So one thing to be careful of when we're using instrumental color assessment is that the delta E, the color difference, only tells us how big the color difference is. It doesn't tell us what makes up that color difference. To do that, we have to look at the individual delta L star, delta A star, delta B star. As we can see in this example, we have a delta E of 2.28, but that would just tell us if our tolerance was set at 1 or 2, then that would be a fail. If we had a delta E star of maybe 5, then that would be a pass. Obviously, if it's a fail, it becomes more critical. What is making that color difference? So we can look at the L star, A star, and B star differences here. We can see that we have a delta L star of minus 1.7, a delta B star of minus 1.5, and a delta B star of 0.45. Actually, if I look at that, it's, yeah, the delta L star is saying that it's darker. We've got a slight typo there. The delta A star saying that it's 1.45 less red, and it's slightly more yellow. So the main issues here are the L star and the A star. So we could go back to the laboratory and with that information, then make an adjustment to the formulation. So actual tolerancing itself. So I've touched on very well the different types of color scales. If we stick to the C-Lab system, within the C-Lab space, here we have on the right side the A star and the B star axes, and the if you like the color circle. We can look at point A as being obviously the L star comes out of the screen and through the screen, so we're not seeing that third dimension in this particular schematic, but we have an L star of 50 units, so that would be out of the screen towards us, an A star of 9, so it's slightly towards the red side, and a B star of 54, very much in the yellow direction. Alternatively, we can look at that as, again, the L star being the same, but the C star, the chroma, which is the vector from the neutral point out to the A point of 54.7. The higher the C value is, the more chromatic or stronger the color will be. And then we have a hue angle of 80.5. 0 is red, and if we work anti-clockwise around the color circle, we go through all the other colors within the spectrum. And similarly for point B, the L star is common to both of these descriptions. We have an A star of 50, again, in this case, very red. We have a C, which is 54.6, so a similar strength of color as the point A, although we're talking red here rather than a yellow. And the B star, 22, and also the hue angle of 23.8, which means it's much closer to that red axis. So we can use LCH for high chroma colors, and LAB can be used for more achromatic colors. If we compare these two color spaces, the importance comes when we actually set tolerances within it. The C-Lab space gives us rectangular tolerancing. One thing that was shown very early in the life of the C-Lab color difference is that the human eye does not pick up colors rectangularly, so there is a certain degree of error between what we will see visually in the light box and what the mathematics will report as a pass or fail. One way to try and eliminate some of this error is to look at the LCH, which is, well, unfortunately, this is a very American word, which my accent has great difficulty getting around, but it's a trapeze shape rather than a rectangular shape. And then the delta E works in a spherical tolerance. So we have three different spaces there, all of which will not necessarily, overlap 100%. As I said before, the human eye has got elliptical sensitivity. So in this case, if we were in a yellow, which is we are quite forgiving in our visual pass-fail would include almost all of these different shapes, but obviously in a more critical area of color space, the mathematical solutions might fall outside of the area the eye would be would say a pass in and or a fail. So if we set that delta E too large, obviously you can see here there's quite a big area where the mathematics would say pass, and visually we wouldn't. So as you can see here, if we use the L star, A star, B star tolerances, that rectangular box is significantly larger than the visual ellipse. We use LCH, as you can see, we still a degree of error, but it's much, much smaller. Okay, this might help inform me going into the next few slides, which to concentrate on. What type of tolerancing are you guys using at the moment? Is it the rectangular or trapezoid, the spherical, or the elliptical tolerancing?
Okay, thanks, Colin. I'm launching the poll. All right, let's give a few seconds to our audience. All right, a few more seconds. Okay, people are still voting. All right. Okay, I'm gonna close. Okay, I'm gonna close the poll and we're gonna analyze the results. All right, so I'm sharing the results. Colin, can you see it?
Unfortunately, no.
Okay, so we have the highest rate is 45% spherical, and then we have 27% for elliptical and 27% for rectangular trapezoidal.
Okay. Well, that's an interesting spread. That's
Okay, we're back to your presentation. If you can,
okay.
if you want to comment.
I'd say that's interesting. Maybe everyone was struggling to understand what the questions meant, but that suggests that we've got a lot of people using, well, my take on it is a lot of people using delta E as a sole arbiter of pass-fail. Obviously, some people using elliptical have moved on to, as we shall see in the next few slides, some of them, the advancements have been made in the mathematics since the CLAB color equation came in like the late 1970s. So let's move to the next slide. Elliptical tolerance improvements. As I said before, we had the CLAB mathematics were published 1976. Very quickly it was seen that there were limitations using the tolerancing on the L star, A star, B star, how it did not agree very closely with our vision. Ironically, that had been discovered way back in the 1940s with experiments that were done in America that determined that our human pass-fail perception was elliptical. So obviously, different industries with uptake of instrumental color measurement at different times, there was a certain degree of politics, I guess, was involved in that, with different equations being offered within different industries, especially in the textile industry. Some of the end users had their own bespoke equations which they would offer to their suppliers, but were not readily available to non-suppliers, let's say. And then the paint industry was using probably working with C-Lab a bit more. It wasn't really until into the 1980s that new equations started to come to the fore that used the elliptical tolerancing. The foremost one of those being the CMC color different equation, as published or developed by the Society of Dyers and Colors here in the UK. The two things that equation looked to overcome was one, the elliptical tolerancing versus rectangular, but also that our eye is more critical in certain areas of color space than in others. This diagram here shows to a certain degree that certain areas of color space here are bigger than others. We can see here our eye is very forgiving in the yellow region. So if you have a color and you try to match it and you're on the yellow side of that color, you can go a long way yellower and the human eye will not pick it up. If you go slightly to the blue side, yeah, it will scream at you a fail. But on the other side, if we look in a gray, so we have a delta E here of 3 in a bright yellow, it's invisible, as I say, and that would, in the CMC equation, would equate to a delta E that was probably less than 1 based on the mathematics there. If we look at a gray for that delta E of 3, huge difference, and the delta, the C-Lab equation, the CMC equation would give us a much higher value. Each of these ellipses in the right-hand diagram equate to a CMC delta E of 1 unit. So you can see around the periphery, they are very large and quite fat ellipses. As we get to the center, they get much, much smaller. So we're getting much more critical as we get towards the neutral point. So a nice little slide here, which showing the agreement between the mathematics and the visual. C-Lab, as I say here, or CIE 76, as some of the people within the printing fraternity are probably more familiar, we only have 75% agreement between the mathematics and the visual. Now, if you're working in a lot of colors that are quite so deco paint, for example, a lot of paint companies find that C-Lab works okay for them. They don't get too many disagreements between the visual and the instrumental. And if they do, if they're aware of this limitation, they can still work well with this equation. But obviously, if people are not so familiar with the limitations, then this could be a big problem. We then move through to the CMC, and we've put here CMC 2:1. This is just the CMC can be set up as CMC 2:1 or a 1:1 ratio, which basically allows a weighting factor on the lightness. It was determined when this was first written that when we look at a color match, when we tolerance a color, we do two things. We say, can we see a color difference, yes or no? And if we can, is it an acceptable color difference? For many people, a perfect match is either seen as not achievable, which is quite realistic, but there is a certain degree that we can accept or not. So a 2:1, which is typically used within the textile industry, where they work to an acceptable color difference, we have about 95% agreement with a visual. The paint industry normally, if they use CMC, will work to a 1:1 ratio where lightness becomes more critical, and therefore our color differences will be much tighter. And of course, the most recent CIE standard is the CIE 2000, which we have over 95% agreement with the visual. Now, all three of these, C-Lab, CMC, Delta E 2000, my personal experience is that all three of those are currently used within the industry, certainly the industries that I work in. C-Lab has been around since for like 35, 45 years now. It's used quite widely. If it's used correctly, that can be quite successful. CMC probably has obviously significant improvements over C-Lab, and there's been quite a lot of uptake in the last 10 to 15 years. CIE 2000 much newer equation. I think the CIE only actually published it as a standard in 2013. So it's much newer, much lower uptake, because many companies, for good reason, don't wish to re-establish all their tolerances, which they've been using for many, many years. CIE 2000, again, only my experience seems to be that it's used quite widely in the printing industry, where there is a less legacy of color measurement. It's been more process control in the past with more densitometry. So more recent use of color measurement means that there is like a blank sheet. So you can use the latest, greatest color equation without any fear or hindrance from either supply chain or legacy data. Oh, okay. So this is where we could go on for the rest of the day talking about where I should set my tolerance. This is a question I get asked almost all the time, especially when we do our fundamentals of color presentations. Is there an international standard on tolerancing? No, not that I'm aware of. I've never come across one. It will depend on the nature of what you're producing, the shape, the size, the adjacent materials. Are the two colors going to be touching directly? Are there gaps? And the one point we probably haven't mentioned here is what your customer will accept at the end of the supply chain. So yeah, there's many things or dimensions we have to consider when we're setting these values. Here's an automotive example. For any of you from the automotive industry on the call would know this well. I'd say, look at all of these car pictures. We put a black line on each of the diagrams. Can you see the differences, or is there any differences between the different parts, the wing and the bumper, the wing on the body panels? It could be, I'm guessing most of you might see one or two, but you might be saying it might just be the shadow, how it's cast on the car. If we take that line away, now you can see quite readily, especially in the bottom central picture. I think that's probably the most obvious one, where there's quite a considerable color difference. We go back and put the line back in, it's less easy to see. So if our components are separated by some other color or some space, our tolerances don't necessarily have to be as tight. If these parts are in a car body going to be exactly together, or in a garment going to be a sleeve against a body panel of a shirt or a jacket or something, if they're going to be within some printed material where the colors are going to again be directly against one another, the tolerances therefore take on a much more critical dimension. I quite enjoy when we have a mixed group, again, in our seminars, if we get people from the auto refinish industries and from the printing industry, and then ask them what tolerances they work to. Sometimes we can have a magnitude of 10 difference. The auto refinish might work to a delta E CMC of 0.2 or 0.3, whereas a printer might work to something that's more like 3 to 5. Each industry will look at each other in horror or amusement, but I would say both are correct, because they fit those particular criteria for the customer expectation from those products in terms of the nature of the product, where they will be seen, how they will be seen, and etc. Okay, here we have two computer screens. Okay, they won't necessarily be seen against one another, but you can see the color difference in them. Would it be critical? If they're going to be seen like this, yes. If they're going to be seen further apart, obviously not. Actually, that's car rear view mirrors. I apologize. I have seen one similar, which is computer monitor stuck side by side. So unless you have two rear view mirrors in your car, then the delta E might be slightly less critical. Obviously, there's also a difference between the back side of it and the front edging. So that would be a more critical color difference there. Okay, we change the light source and we see, wow, there is a very big difference between the front and the back panels now. So although we wouldn't see both of those mirror components together, we would certainly see the difference between the front and the back components there, which obviously going to give the impression to the customer probably of low quality in terms of the overall product, or yeah, just unacceptable quality control. So if we look at a more slightly three-dimensional illustration here we have a color called firecracker. And we have a light dark and red green and yellow blue dimensions to it. If we put a slight separation line in, we can probably tell there is a color difference. The degree of it or how critical it would be might be more difficult to come to a firm conclusion on. But if we take that separator line out, we can see for sure that that light dark is really, really bad. Again, if we go back one, we would say it's not acceptable, but well, it's not a perfect match, but is it acceptable? Yes or no? Again, if we see them directly touching, that would be completely unacceptable. And the blue probably isn't very acceptable either. So again, that just shows the context in which we look at color. If they're touching, much closer tolerance is required. If there's a slight separation, we have a little bit more scope to play with. So here we have the tolerance food chain, if you like, which I always say to customers when we're doing our training on our software products, when they ask me what the tolerance should be, I say, okay, you've got your customer requirements. You have a specification that might be sent down to you from a marketing company or branding or a design house. Where are they getting their tolerances from? Are they literate in color? Do they know, maybe they have heard from somebody who heard from another person who went to a seminar, or maybe someone read a book, what a tolerance should be, but that is not necessarily going to be a good fit for every application in every industry. You then have within your product, how variable will that product be? If it's a dyeing, you have water and heat involved, which are sometimes not so easily controlled. If you're in plastics, you have the heat and the molding. In your paint, you maybe have the weighing, the mixing, the drying, it's accelerated drying times, etc. All become variables within the process. We can obviously use instrumental color assessment to put a number to each variable within the production stage, which will allow us at the end of the day to be more informed about the variation within our process. Is it acceptable? Does it fall in line with the customer expectation? Is there anything we can do to improve our production? Maybe the equipment is a bit old, or maybe the operators need better training, or maybe we have to just go back to the end customer and say, okay, you've asked for a delta E of 1. Our production gives us a variable of 0.8. Really, we have, that's going to be very difficult for us to achieve on every batch we do. Does the customer accept slightly more than 1? In which case, we have a better ability to meet your expectation. Or maybe we have to improve our production variables, so we have a delta E of 0.5. Okay, 0.5 to 1, we have a better variable there. And obviously, the instrument, at the end of the day, the instrument we use to measure the color, is there a variation there? We can, again, assess all of these and build a better picture, which allows us to build a better tolerance within that. So talking about the different solutions, touching on the instruments there are different instruments for different types of production based on either where they need to be in the factory, or do they need to be transportable between customer and the production plant. What is the nature of the product? So for example, here's some of the X-Rite instruments. We work from the left-hand side. We have the benchtop sphere instrument, very sphere-based technology used very commonly within the textile, paint, plastics industries. Benchtop instruments will obviously give a higher specification. They're more stable. All the optics are bolted onto optical benches, so much more stable, repeatable, a number of much greater flexibility in terms of aperture size available. You can do transmission measurement for translucent plastics or for liquids. Quite often these days, we are asked to measure things, fruit juice, alcohol, different maybe effluent solutions from washing or from dye house effluent, things like that. All a benchtop instrument would give us all the capability there. A number of different instruments within the benchtop ranges, again with varying price points. Then a customer might want to use a sphere type instrument, but okay, the repeatability might be slightly lower, but they want the flexibility to be able to take that instrument out to a customer site to do if a customer is arguing that some production pieces come in and the it's not within their perceived specification. Instead of having to go to the expense of recalling that piece, someone can go out with a spectrophotometer and measure on site and see whether it is a genuine problem or maybe just an inaccurate expectation on behalf of the customer. We have spoken to many customers in recent times who have products, for example, architectural products, which would be very expensive to recall and check and find that maybe a piece has just been positioned wrongly and there was maybe a texture effect on it which made it look wrong in place. For example, roof tiles or ceiling tiles, sometimes they have quite a significant color change based on the texture of them, so they need to be fitted in a particular direction so they always look matching. That can be easily checked on site using a handheld instrument, which will have onboard software, but also can link into a PC-based software, so you can bring it back to base, plug it in, download the data, and then do much more sophisticated analysis on the PC. Or as you can see here, you can get a very simple pass-fail tick or cross and some LEB delta E values on the instrument itself. Then we move to our MAT, multi-angle spectrophotometer, used for metallics, for automotive refinishes, anything where you have a color change with angle dependency. You could use a multi-angle spectrophotometer. We sell them in 3, 5, 6, or 12 angle configuration, depending on the requirements. And finally, new instrument for us, the MetaView on the right side, non-contact 45-degree spectrophotometer, which is essentially an imaging spectrophotometer. This measures in a slightly different way to traditional spectros, where we would shine light into an integrating sphere onto a sample and recall what comes back, or to shine the light at, say, a 45-degree angle onto the sample and measure at 0 degree. What the MetaView does is basically takes a very high resolution photograph of the sample, analyzes that data to create a spectral reflectance curve, which can then be manipulated using CLAB, CMC, Delta E 2000, and various other color metrics. The great benefit of this type of technology is we can, instead of having fixed aperture sizes, we can zoom from a 12mm down to a 2mm spot and move the spot around the sample to pick up the best area of a sample drawdown, or a textile sample, or maybe a particular color within a printed image. Today we sell that a lot with retail paint solutions for DIY stores, but are also selling it to companies that are doing things like marbleized worktops or flooring, wooden finishes, where we need to zoom in on very critical areas of the color. All will offer slightly different solutions, but will present the data to allow us to work with the different color equations and set our tolerances. as I've said before, based on our industry expectations. There is software packages, obviously, to go with all of these. Color iMatch, which allows us to do quality control, formulation, and correction, which will link with the sphere-based benchtop spectrophotometers, the portable sphere-based, and the METAView spectros. There are a couple of other portable spectros that are the Exact, for example, which is used primarily in the printing industry, which again can work with the Color iMatch or the Color IQC software. Again, Color IQC, unlike what it says here, is matching software. It should actually be quality control software. It is the quality control element of the Color iMatch software. So a customer or a company can start with IQC to do color pass-fail, and at a later point, if they decide that their application would fit doing their own in-house color matching from their supplied colorants, they can then upgrade to the Color iMatch. There is also a net profiler tool which allows companies which have multiple instruments, either internally or within a supply chain, to profile these instruments so that they give an even greater inter-instrument agreement, so that there's a better chance to share digital data. So you can measure a standard, let's say in the Far East, in a production area, plant maybe in China, that can then be electronically emailed or sent or shared within shared files on an internet to, let's say, a specifier maybe somewhere in Europe or the US, and they can manipulate that data as if they were measured it directly in their own laboratory. So all of these tools will allow us allow us to do digital color tolerancing, color communication, but also help us improve that. And obviously I can't remember, back to the first question, maybe it was 8% of you were still only maybe doing visual color assessment. We have, from X-Rite's point of view, we have the SpectraLite QC and the SpectraLite Judge QC light booths, which allow us to do the visual assessment under a whole range of light sources, D65, TL84, cool white fluorescent, with and without UV, which is obviously very important for textile users. And this can be used either standalone or can be used in conjunction with the instrumentation, so that we get the benefit of the visual assessment as well as the numeric assessment. Quite conscious that we're getting quite on in the hour's presentation, so we'll leave enough time for some of your questions. So maybe you answered this question as part of the first question, but are you currently using controlled lighting, either as part of your QC procedure or internally within your laboratories or your factory?
All right, thanks, Colin. I'm launching the poll. Okay, let's wait a few seconds. All right. Okay, easy question to answer. Seems like everybody answered. I'm going to close it and comment the result. So I'm sharing the result, and we have 95% of yes.
That is an answer that makes me very happy, I have to say. Yeah, that's very good. And for the other 5%, okay, thank you. For the other 5%, I would strongly suggest that you consider introducing controlled lighting. Many companies will do that through like buying a light box. Some will go slightly grander scale. For example, the automotive industry will have color harmony rooms, which are really a large room, which basically the room becomes a light box into which you drive the car, and you can do all the visual color checks within that room. And just as a final slide of the presentation, X-Rite does also offer seminars, fundamental seminar, fundamentals of color and appearance, of which really I have taken pretty much today's presentation is a section of that where we talk about what is color, how we see color, so that we understand our own limitations, how we introduce controlled lighting and all the elements of that and the considerations, and then through the color equations, far more detail on all these different color formulas and how we should implement them, and of course how we should set up tolerancing, or what we should think about when we set up tolerancing. And there's also a fundamentals of instrumentation seminar, which takes that onto another stage, purely talking about use of instrumental color control. So thank you very much for your attention. I hope that has been of interest to you all, and maybe raised some questions in your own minds to go away and review your current setup, or maybe even just confirmed that maybe what you're already doing is on the right track. Hopefully some of you might have sent in some questions to Jessica while we were talking, so I will wait to see if I can answer any of those.
All right, thank you very much, Colin. So yes, we're going to begin the Q&A session. So as a reminder, you can still submit questions through the questions panel in your attendee control panel. So please don't hesitate, type in your question. We do have some. So first question is, how do we assess color appearance in LED lighting? Illuminance, CIE have not yet standardized.
Well, we have introduced our IQC10 software only a couple of weeks ago, and we have a whole range of, as I understand it, LED sources within that package for that very reason, because it is becoming far more requested. Even a lot of the laboratories and offices I go into these days are now LED light set up. So yeah, I'm not entirely sure. I thought the CIE had started to what's the word I'm looking for, to publish some of these LEDs, but that's something I need to go away and check for sure.
All right, another question, a bit technical. Could you please give more detail why the human eye is ellipsoid tolerance shape?
Okay. I don't know the actual biological reasons for it. It will be down to somehow how the brain sort of interpolates the information that comes from our rods and cones. How it was discovered was an American scientist called McAdam in the 1940s basically got a whole range of pairs of samples and mixed them all up and got people who were not trained in color assessment to pair them up. Once they'd done that, he then plotted the coordinates of all these samples, and he came to the realization that we toleranced visually elliptically. Yeah, that's probably more of a historical explanation rather than a scientific explanation. I would probably need to go away and try and find some reference in one of the many textbooks which are available to find some more details on that. So I can have a look and see if I can discover anything. Maybe it could be if you can find McAdam's paper from around about 1942, probably that might contain an answer to your question. I will need to try and dig it out myself, to be honest.
Okay, Colin. Next question. What is your plan to add LED module in Exact? You mentioned Exact earlier, part of the instrumentation. So Here's a question.
Okay, we need to get back to you on that. Obviously, as these new illuminants are and new color equations do become standardized, our firmware in all our instruments and our software platforms do get updated. I don't know personally what the schedule is for the exact. For anyone using our CI6 Spectra, I know there is a firmware update planned for later in the year, which I guess would include the LEDs, but the exact works to different timescales. So I would need to check that, and we can let you know.
Okay, next question. What's the expected delta E difference between exact and I1, as these are different instruments?
It'll be nice when I get a question I can actually give a definitive answer for. Because they're different instruments, they're probably not particularly close, but again, that's something we could ask the question of our instrument product managers and get back to you on.
All right. Colin, what would you suggest if we get color match visually, but delta E is more than 2.5?
Well, if they are visually passing, 2.5 is obviously okay. I think that's the rule of thumb I normally use with people is if you visually pass a color, then the numbers you get should be right. As I said before, the tolerance, the numbers for someone to say 1 is a pass across all industries is completely wrong, because for some industries, like 2.5 would be fine. So yeah, if you are visually okay with that color, then that number is okay to go forward with. I've always told people, if they get a disagreement, if they get a number on in the mathematics that says pass, and they visually fail it, I would always say go with what your eye tells you. So equally the other way, if the eye says pass, whatever the number that comes up, I would say probably that is good to go with. There is a certain amount you would probably have to go back and check over a number of different colors that held for all of the colors, or repeat batches of the same color, just to make sure that that particular day wasn't a day where you were maybe being a little bit more forgiving in your visual assessment than another day, and what conditions you were checking the color under. So I wouldn't necessarily just say, okay, 2.5 is fine, we'll go with it. I'd do some checking to make sure that you are comfortable that number would be okay across either across all products or across specific products. Hopefully that answers your question.
Okay, next question. Sometimes the CIE 2000 result is shown in the tolerance label like 1.6 delta E, but we're seeing a huge shade variation by eye under light box. So how to solve that? My CIE 2000 ration is 111.
Okay, sorry, say that. So you're getting 1.6 and delta E 2000. What did you say the shade variation was that? Sorry, could you repeat it?
Sure, that's correct about the 1.6 delta E. We are seeing a huge shade variation by eye under light box. How to solve that?
Okay, are you checking? I mean, the first question I would say then, are you checking for METAMERISM? Are you looking at under different light sources? Because obviously, if you have it set with all color difference equations, and this is not just CIE 2000, it'd be for all of them. Many people will just do a test under the first light, which might be D65 or D50, or a fluorescent source, and they'll get a pass. But obviously, if that color is metameric, it would appear there'll be a shade variation under different lighting conditions. So really, you either have to set your pass-fail under more than one light source or include your metameric index as part of the numeric color assessment. Again, I can only speak for the X-Rite software. Within our IQC, we can have your delta E under whatever formula with the LAB or the LCH, but you can also include things like METAMERISM index, opacity, and various other color indices. But METAMERISM is probably a very important one to check.
Okay, Colin, I think, so this person is adding a comment. It's actually the same light, but the delta is under 2, but they're seeing shade variation.
Which suggests the delta E2 is probably too high then if it's a pass, or if it's set to say that 2 is a pass. If they're seeing shade variation, they probably have to tighten up that tolerance.
Okay, we have 2 minutes left. Important question. Where can I get guidance on changing from LAB to LCH? And is it possible to run color iMatch software using both?
You can get both in the color iMatch software. Where to get more information on it, I'm guessing come along to one of our Fundamentals of Color courses. We'll talk all about these things.
All right, next question. Given the elliptical nature we perceive color, should the delta E tolerance vary with chromacity? So grays have smaller tolerance than high chroma colors?
Depends on the equation you're using. If you're using the C-Lab equation, yes. If you're using CMC or delta E 2000, because of the internal mathematics changing the shape and the size of the ellipses, a single number tolerancing will work for the high chromatic and the more neutral colors.
All right. Okay, we might have time for one last question. What tolerance would you recommend on textured materials, for example, corrugated boxes? Should this have a tighter tolerance?
Again, I don't think there's a definitive answer to that. It would depend what the final usage for the corrugated cardboard is, for example, or the product. If it's a high-end product, then obviously the tolerances would need to be tighter than if it was in just, let's say, mere packaging. Again, what is the expectation of the customer? Obviously, if there's a texture, maybe the orientation of the color difference due to the orientation might have to be taken into account. Obviously, when we measure things like textiles, where you have the weave of the textile, we normally recommend that you take an average of a measurement at, say, 0 degree and 90 degree. It might be that for the corrugated material has to be considered as well. And I guess a bit of experimentation to find out what numbers will fit with the customer expectation, as kind of we've been saying again and again during the last hour. I think it will, in the end of the day, the numbers will be determined by what the customer says they're happy with.
Okay, thank you, Colin. That's the end of the webinar. We do have a couple of more questions, but we will answer them by email, no worries. Okay, so I'd like to thank Colin for this interesting webinar and everyone for attending today. So if you have any other questions, please contact us anytime. On behalf of X-Rite Pantone, thank you for joining us today and have a great rest of your day. Thank you.